One feature changed everything. Before we understand why modern system design looks so different, we need to understand the architecture that powered the internet for decades. At first, everything was beautifully simple. The application becomes popular. More users sign up. More requests arrive. The architecture doesn't change, but the workload does. Instead of asking for a list of movies, users now expect something completely different. They want explanations, comparisons, personalized recommendations, natural conversations. This isn't just another API endpoint anymore. AI doesn't increase complexity by 10%. It changes the economics of every request. Latency increases. Compute costs explode. Memory usage climbs. Suddenly, engineers are solving an entirely different class of problems. A traditional application usually follows a predictable path. A request comes in, data is fetched, and a response is returned. AI systems are fundamentally different. Before an answer can be generated, the system must think, retrieve context, build prompts, perform inference, and stream results back to the user. Here's something that surprises many engineers. Large language models don't continuously search the internet or your company database. They only know what they were trained on. If you want accurate, up-to-date answers, you have to provide the missing context. Instead of expecting the model to remember everything, modern AI systems retrieve relevant information first. Only then is the prompt constructed and sent to the model. This technique is known as Retrieval Augmented Generation, or simply RAG. Unlike traditional software, AI systems consume resources continuously while generating an answer. Every additional token increases computation, latency, memory usage, and ultimately cost. Efficient system design is no longer just about speed, it's about managing intelligence efficiently. Everything we've seen so far works beautifully, until it doesn't. Imagine millions of users asking complex AI questions at the same time. Every request competes for limited GPU resources, and suddenly, the real challenge isn't intelligence, it's scheduling. Not every task needs to finish immediately. Some jobs, like generating reports, sending emails, indexing documents, or creating embeddings, can run in the background. Instead of blocking the user, engineers move these jobs into queues where workers process them asynchronously. At scale, failure isn't an exception, it's inevitable. Servers crash. Networks become unreliable. GPUs overheat. The goal of system design isn't preventing failure. It's designing systems that continue working when failure happens. Running an AI model isn't just about having a powerful GPU. Memory is carefully divided between model weights, activations, the KV cache, embeddings, and system overhead. Understanding this distribution is critical when designing efficient inference systems. Imagine a user reports that the AI feels slow. Which server is responsible? Which GPU is overloaded? Which database is delaying the request? At this scale, guessing isn't engineering. Modern systems have to explain themselves. Modern engineering teams don't monitor one number. They collect thousands of signals every second. Together, these metrics tell the story of the system's health long before users notice anything is wrong. Once a system understands its own health, it can begin making decisions automatically. Instead of waiting for an engineer to wake up at 2 a.m., the platform continuously adjusts itself as demand changes. System design didn't change overnight. Every generation of architecture solved the biggest problem of its time. As applications evolved, so did the systems that powered them. None of this is just theory. Netflix publicly documented its move away from a monolithic application years ago. As its global audience grew, it embraced microservices, cloud infrastructure, intelligent caching, regional resilience, and massive content delivery networks to keep streaming fast for millions of viewers. The next generation of software doesn't simply generate text. It plans, remembers, calls tools, makes decisions, and completes tasks. That changes system design once again. A chatbot waits for instructions. An AI agent breaks problems into smaller steps, decides which tools it needs, gathers information, evaluates results, and only then responds. The architecture is no longer a straight line, it's a reasoning loop. Large language models have limited context windows. Modern AI systems constantly filter, rank, compress, and prioritize information before it ever reaches the model. Traditional software forgets every interaction once a request ends. AI agents don't have to. Memory allows the system to remember previous conversations, user preferences, unfinished tasks, and long-term objectives. Put everything together, and the architecture looks completely different from the systems that powered the early internet. Today's platforms combine traditional software engineering with inference pipelines, memory, retrieval, observability, autoscaling, and intelligent orchestration. Let's go back to where we started. One browser, one server, one database. Over the last few minutes, every new component we've added solved a problem we witnessed. Modern system design didn't become complicated by accident. Every layer exists because something simpler eventually stopped working. What used to be one database query has become a coordinated conversation between dozens of specialized systems. Each component does one job exceptionally well, and together they create the illusion of a single intelligent assistant. Not every stage of an AI request costs the same. Most of the compute is concentrated around retrieval, prompt construction, and inference. Good system design minimizes unnecessary work before expensive computation even begins. Experienced engineers don't begin by choosing Redis, Kubernetes, Kafka, or vector databases. They begin by asking a much simpler question: where is today's bottleneck? The technology follows the problem, not the other way around. Users never congratulate you for choosing the right architecture. They simply notice that everything feels instant, reliable, and effortless. That's the paradox of great system design. The better it is, the less anyone notices it's there. AI is still in its early days. Context windows are growing. Models are becoming faster. Agents are becoming more capable. But one thing won't change. Every new breakthrough will create new engineering problems and new system designs to solve them. We started with one browser, one server, and one database. Every layer that followed solved a real problem created by growth, scale, and intelligence. That's the real lesson. System design isn't about memorizing technologies. It's about understanding why they exist. And as AI reshapes software once again, that way of thinking has never been more valuable.